we have theorem 18 for next. Here we have three topological spaces a comma tau, x comma sigma and y comma mu. The sets are a, x and y and the respective topologies are tau, sigma and mu. And then there is a function f from a into the Cartesian product of x and y such that for any point a from the domain a, f of a equals this ordered pair. Any output of f is going to be an ordered pair because it's an element in this Cartesian product. And that ordered pair has coordinates given by two other functions, f1 and f2, where f1 maps a into x and f2 maps a into y. If so, then f is continuous if and only if these two functions f1 and f2 are continuous. That is the claim. Continuity of f1 and f2, obviously you understand what that means because a, x and y are topological spaces. What about continuity of f? A already has the topology tau. What topology do we have on this Cartesian product? That is the product topology that you derive from sigma and mu. So let's now prove this theorem. We start the proof by assuming that f is continuous. We will now prove that f1 and f2 are also then continuous. We next define two functions, pi1 and pi2. Pi1 maps x times y into x and pi2 maps x times y into y. What pi1 does is it gives us the first coordinate of any point in x times y. X times y, this point gets mapped onto the first coordinate and pi2 gives us the second coordinate. Now next our aim is to show that these two functions are actually continuous. So to show that pi1 is continuous, you take any open set in x, that means u will come from the topology on x, so let u be any element in sigma. And then calculate the inverse image of u under pi1. It's not difficult to see that this inverse image is just u times y. I mean, what is this inverse image? It is the set of those points in x times y on which when you apply pi1, that final result is in u. So obviously it will be this set. However, this is open in x times y. Actually, this is a basis element for the product topology on x times y. But anyway, it's open. So that is why pi1 is continuous. Similarly, pi2 is also continuous. Now next, the key observation is this. Those functions f1 and f2 are actually, they can be given in terms of pi1, pi2 and f, like this. f1 turns out to be the composition of pi1 and f, and f2 equals pi2 composition f. Let's see, for example, how this one is true. So we get a hint that this equation can possibly make sense from this diagram. F maps a into x times y, that is already given, and the way we define pi1 maps x times y into x, and our function f1 in the statement of the theorem maps a into x. So this may be true, okay. From this at least we see that it may be true. Now is it really true? When we compose these two and apply that on any element of a, whatever output we get, is that the same output that f1 also gives us? So we do that and see if we really get it. So we take any element a in a and then apply this composition on a. By definition of composition, this equals pi1 of f of a. And now you recall what we have in the statement of the theorem. F of a is this ordered pair, f1 of a comma f2 of a. And then pi1 gives us the first coordinate, which is f1 of a. So yes, they are the same. Whatever pi1 composition f does to a, f1 does that same thing to a. So yes, this is true. Similarly, this one is also true. And that is why f1 and f2 are continuous, because continuity of f is our hypothesis in this part of the proof. And we have just now proved that pi1 and pi2 are continuous. And previously we proved that compositions of continuous functions are continuous. So that is one half of the proof. Now we are going to prove the converse. Now conversely, let f1 and f2 be continuous. We have to then show that f is also continuous. Now we take an open set u in x and an open set v in y. That means u comes from sigma and v comes from mu, the respective topologies. Now the hypothesis that f1 and f2 are continuous gives us this, that f1 inverse of u and f2 inverse of v are both open in A, because recall that A is the common domain of f1 and f2. So both of them will belong to the topology on A, that means tau. And that is why their intersection will also belong to tau. And finally, you note this, that this intersection is actually nothing but the inverse image of u times v under f, the original function. I leave it to you to show why these two are equal. I mean, it's a set theoretic thing. You take a point here, show that it's here, and vice versa. And that is why f is continuous. How? Well, what type of set is u times v? It's a general basis element in the topology on x times y. And when we defined continuity, at that time itself we understood why it's enough to show that inverse images of basis elements are open to show that a function is continuous. So that is why f is continuous. So here the proof ends. Next we have a small example, example 9. In calculus, when you study calculus, you come across parametrized curves, which are curves where, these are curves which are traced by a moving point, and that moving point depends on a parameter. The parameter is a variable which takes its value from some set. As the parameter value changes, the location of the point changes, and that's how the point traces the curve. So a parameterized curve is defined. I forgot to write parameterized curve in the plane. Okay, in this example it's about plane curves. Is defined to be a continuous function, gamma, from a closed interval, closed bounded interval in the real line into the plane R2. You see this condition, continuous function. This ensures that the curve is in one piece. Now, there of course is a definition of continuity for this type of functions that we use in calculus, and that continuity comes under our general topological definition and is related to what we did just now. So such a function gamma takes on this general form. If you write the function gamma, because the outputs are going to lie in the two-dimensional plane, each output is going to look like this, as an ordered pair of real numbers, where the x and y coordinates are both functions of the parameter t. Now, continuity of this gamma, according to the theorem that we saw just now, is tied to the continuity of x and y. Gamma is continuous if and only if x and y are continuous. So this is what happens, what I said just now, that as t varies over this interval, a point gamma of t moves in the plane in whatever manner it moves, according to this function, and traces the curve. It may be a closed curve also if gamma of b coincides with gamma of a. It may also intersect itself, anything can happen, okay, but the fact here is that because gamma is continuous, it will be in one piece. Exactly why, that we will see when we study connected spaces. That is coming in the next chapter. And then in the same example, the author mentions also vector fields. Similarly, a vector field in the plane is a function of this type, where the inputs are vectors, that means points in the plane, and outputs are also vectors. So here the components of this vector v are these functions p and q, which are real valued functions, but the inputs are points in the plane or vectors. If instead of writing this in vector notation you write it as a point, then it will look like this. For example, you have some kind of force field in the plane, okay, so that at every location in the plane a force is felt by something. So those are this type of functions, and their continuity depends on continuity of the components. They are continuous if and only if the component functions are continuous. You may have seen this elsewhere, where continuity of this type of functions is defined in terms of continuity of these two. That is what we wrote in that theorem as our claim, that itself is taken as definition of continuity. Besides all these techniques of creating continuous functions that we have seen so far, you also find this in calculus, and especially if you study differential equations, that if x is a set of real numbers, a subset of R, and you have two continuous functions f and g which are real valued and both have x as their domain, common domain, then f plus g, f minus g and fg are also continuous. Algebraic combinations of continuous functions are continuous. And also, as you already know from calculus, that if the function g never vanishes on x, g of x is not equal to 0 for all x coming from x, then you can consider this quotient of f and g in that order, that is f divided by g, that is also continuous. We are going to generalize these results from calculus to our general topological setup appropriately in the coming sections. Another way of producing continuous functions that you are familiar with from calculus, or more accurately from analysis, is this. Say you consider a sequence of functions. Don't follow this notation, okay? I just wrote it to show everything at once. There is a sequence of functions. What this notation means is that each function fn maps x into R, where again x is a subset of R. Each function is continuous and the sequence converges uniformly. This is important, okay? Uniformly to some function f also which maps x into R, then f is continuous. Now this result of course is nothing new to you. You already know this from analysis, and it is used, for example, to show that functions like this are continuous. The sine function, for example. Instead of relying on geometry to define sine function, one can analytically define sine function using this infinite series. X minus x cube over 3 factorial plus x to the power 5 over 5 factorial and so on. It turns out that if you consider the sequence of partial sums of this series, then you get a sequence of functions like this one, where each function is a polynomial, so obviously continuous. It turns out that this sequence converges uniformly to a function, and we call that function sin x. So that is why by this theorem sin x is continuous. We are going to generalize this, not this one of course, this one appropriately to our general setup as well. So the current section ends here. In the next topology video we are going to start exercises.